Hello everyone, I'm Cheng Zhang. Today I'm going to present our paper, MingledPie, Cluster Mingling Approach for Mitigating Preference Profiling in Cluster Federated Learning. This work is collaboration with Yang Xu, Jiang Haotan, Jia Jian, and Wen Qiangjin. So, as you know, federated learning is a distributed, privacy-preserving machine learning framework that involves a server and some class collaborating to train a machine learning model. And in each iteration, class train local models using their private data size, and the server aggregates these local models to form a new global model. This process iterates until the model converges. However, due to the non-IID nature of clients' data, directly aggregating their local models may lead to difficulties in model convergence. To address this issue, clustered federated learning has been proposed. In the cluster federated learning, clans are grouped into multiple clusters based on their data distributions. Within each cluster, clans train a personalized cluster model based on the generalized global model. With this approach, cluster federated learning can avoid the problem of data heterogeneity. However, there are also some privacy inference attacks in the cluster federated learning, and in this work, we mainly focus on the preference profiling attacks. So, briefly, the preference profiling attack is aimed to infer the data distribution characteristics of the client. For example, if a client has a large number of dog images and a small number of cat images, an attacker could infer client's preference is dog. And in the cluster federated learning, we think there are two types of preference profiling attacks. The first involves inferring preferences based on the client's local model updates, and the details of the attack have been proposed in some previous work. And the second is cluster identity-based inference attack, and it is unique to cluster federated learning. So specifically in the cluster federated learning, because each cluster corresponds to data distribution characteristics, we consider an honest but curious server as the attacker, and if the server has the knowledge of the cluster to which a client belongs, it can associate the cluster's characteristics with the client's identity, thereby inferring the client's preference. So, for example, in an image classification task, the server publishes a set of training clusters in the beginning, and each designed for a specific purpose, such as recognize images with different labels like dogs, cats, and clients whose data distribution are skewed to dog images are grouped into a single cluster. Consequently, a server can easily infer that all clients within the same training cluster have a preference for dog-related data. So we also found there are some exciting methods, such as some secure aggregation federated learning, can resist the first type of preference profiling attack. However, they only protect the client's local models and do not extend their protection to the clustering results. So they are unable to resist the type 2, the cluster identity-based inference. And we also know that some methods use the anonymous communication technologies to break the link between client model updates and client identities. So in this way, even if the server infer private information from the local model updates, It cannot associate this privacy with some specific client. However, this method often requires some additional communication infrastructure, or they cannot to protect communication data. So, in summary, our design goals include protecting preference privacy and ensuring cluster model accuracy and the autonomous deployment without relying on additional third parties. So, to achieve this, the key challenges is how to make the server cluster class and aggregate the cluster models without knowing which cluster the class belongs to. And to solve this, in this work, we proposed the MingledPie, a privacy-enhanced cluster federated learning. Our key idea is like k-anonymity, where clans are mingling to multiple clusters instead of just one cluster. We also propose a cluster model rebuilding algorithm to exclude the mingling error. And in addition, we protect the model parameters with homomorphic encryption. So specifically, we use a client-side clustering algorithm that sends all cluster models to the clans and let the clans to evaluate their true cluster identities. Then the clans train the local models and generate mingled cluster identities based on a false positive rate P. The process of generating false positive cluster identity by client is similar to the public key message detection. It uses a hash function with collision probability P to find other clusters that collide with its true cluster identity, and use it as its false positive cluster identity. So each client builds a cluster identity set, which it includes a true cluster identity and some false positive cluster identities, and the client sends this set and the encrypted local model to the server. During the aggregation phases, the server can build a mingled cluster based on the cluster identity set. These mingled clusters include both true clients and false positive clients. So the server then aggregates the local models from all clients with a mingled cluster to form a mingled cluster model. And as a result, the mingled cluster model can be viewed as a combination of the accurate cluster model and some models from other clusters. Clearly, the mingled cluster models are not usable. Therefore, we need to rebuild the accurate cluster models, which requires the knowledge of the number of false positive clans within each mingled cluster. And we design a method based on the homomorphic encryption. We let each clan to send a cluster identity clue to the server. This clue is computed according to this equation, and the server can aggregate an encrypted mingling coefficient matrix where the diagonal elements are the true size of the cluster and the remaining elements such as x sub 1, 2 is the number of false positive clans from the second cluster in the first mingled cluster. This metric approximates the principal diagonal matrix, and it ensures that the model rebuilding algorithm has a unique solution. So finally, the client can construct a system of linear equations based on the mingling coefficient matrix and the mingled cluster models. By solving this system, the client can accurately rebuild the cluster models. This process iterates until the model converges. And in the experiment, we evaluate the success rate of the attackers' inference of top 1 label on the client. And the experiment results demonstrate that MingledPie achieves a lower attack success rate. And in contrast, client preference in an undefended approach will almost certainly be inferred. We also evaluate the cluster model accuracy on 6 datasets, and the experiment results show that the accuracy loss caused by our defend method is limited compared to baselines. We also prove this in the convergence analysis in the paper. Finally, ablation experiments also show the effectiveness of our cluster model rebuilding method. So in summary, we propose MingledPie to mitigate a preference profiling attack in the cluster federated learning. We can make the server perform cluster federated learning algorithm without access to the local model and without knowing the clustering results. So thank you so much for attention, and I would appreciate any questions and comments that you may have.